Our first speaker following the break is Dr. Deborah Swackhammer. Are you retired or are you still UM? How do you self-identify? UM?
UMN, I guess.
Famously from the University of Minnesota. Slowly extracting herself from that, right? Deb?
So first I want to say I'm just thrilled to be able to be part of this great celebration. So I want to thank Gary for inviting me and the rest of the group that was part of that. Gary asked me to talk about bioaccumulation in the context of the contributions from the Duluth lab. And to really understand that, it's really important. An important part of that story is to appreciate that this lab was established on the Great Lakes. Oh, that didn't work. All right, we'll try this. We'll try this. Oh, I can do that. Okay, that works.
Let's see if this works. I think it goes to sleep or something.
Use the up and down arrows.
Okay, are you dizzy yet? Okay, so the Great Lakes are such a vast body of water that in fact you can see them from space. They're just enormous. And if you look really, really, really closely, you will see the laboratory right there from space on the tip of Lake Superior. But it's important that this lab was on the Great Lakes. So back in 1966, back a ways, and yes, I was born. Whoever looked at me when they accused people of not being born yet, I was at least in grade school. But anyway, back in 1966, a Swedish chemist discovered a complex mixture of chemicals in biota in Sweden, and it was identified to be polychlorinated biphenyls, or PCBs. And that was the first environmental proof that these things were getting into the environment. If you circle back around to North America, DDT had been reported in fish from the Great Lakes from the U.S. Fish and Wildlife Service, but the first report of PCBs in all of North America was by our very own Gill Veith. And Gill had found PCBs in the course of his dissertation research at the University of Wisconsin. Now, from what you know about Gill, so Gill then spent a couple of years getting his dissertation done, and then he worked for a few years at the University of Wisconsin-Milwaukee, and then he joined the new EPA family at the newly established, renamed Duluth Laboratory. And he was very interested in understanding how these kinds of chemicals, if you could come up with predictive tools for how to predict this bioconcentration. So basically EPA had developed a very robust data set of a whole bunch of measurements of contaminants in water and fish done in the laboratory. So they had lots of BSAF data for lots of different compounds that were done and compiled by EPA. And Gill looked at the relationship of this with the octanol water partition coefficient and produced this very iconic, very famous graph. He wasn't the first one to do this, but I just want to point out that this graph, because of the robust data set compared to previous efforts at proving or disproving the thesis that lipophilicity was related to the KOW, that Gill's paper got a great deal of attention. And I also want to point out that this particular relationship and this very iconic figure is still the foundation of bioaccumulation and our understanding and modeling bioaccumulation. It is still the basis of that, even though we've progressed quite a ways from BCF and KOW. Now, at the same time Gill was doing all of this, there was a graduate student at the University of Wisconsin in Madison named Dave Weiniger. But before I get to Dave, let me just point out something. So one of the things that we knew about the occurrence of contaminants in fish, it became quite clear that even though that beautiful graph of Gill's was so wonderful for laboratory data, it didn't predict what was going on in top predator fish in, for instance, the Great Lakes. And so this is just a figure that shows the relationship of PCB concentrations in different parts of the Lake Michigan food web. And clearly there are orders of magnitude difference between the concentrations of the same compound in different parts of the food web. So we knew that it wasn't that simple, that it just was an equilibrium with lipids, and in fact, it was a biomagnification, bioaccumulation issue, not a bioconcentration issue. And in fact, there were lots of papers put out and lots of lead modelers who put together sort of the theory behind what this might look like, what this mechanism of bioaccumulation would look like. And it really had to do with subsequent accumulation in different layers of the food web. And using bioenergetics to predict that. I can't help but point out that I wouldn't have a career if it weren't for that one area that says equilibrium. Turns out that was a really bad assumption, and it made my career. So my little footnote to the picture here. So the first bioenergetics model actually was done by this graduate student at the University of Wisconsin as his PhD dissertation. And Dave and I overlapped at Wisconsin. It was terrific. He's actually taught me everything about PCBs in about 6 months, and that was terrific before he graduated. And he went on to work at the Duluth lab. Gill recruited him from Madison, and he went up to the Duluth lab, and we called it the Madison Mafia. I don't know if EPA knows this, but that's what the University of Wisconsin people called it, because Gill went on to then also recruit Russ Erickson and Larry Burkhart. And so a lot of people from the UW water chemistry program ended up at the Duluth lab. In any event, he then published this model later with an application, and he basically validated the model using Lake Michigan fish data. So this was actually the first bioenergetics model, and Duluth doesn't usually get credit for that, but I think it's important to establish that relationship. Some of the other things that were done in Duluth that were pretty important were to understand that transfer across the Gill membrane. So if you think about those bioenergetics models, first you have to have this uptake across the Gill. And a lot of work was done by Russ Erickson and Jim McKim and also John Nichols. And these papers all came out at the same time pretty much, and it was a lot of intensive work to understand and model the transfer across the Gills. But these models only applied, the bioaccumulation models were only really applicable to non-ionizable, neutral chemicals. And so the question became, what about all those other chemicals that do ionize? And so there were 2 very nice papers put out by Russ Erickson and colleagues that looked at the modeling, essentially, the uptake and elimination of ionized chemicals. So this was, again, a great contribution to understanding bioaccumulation. But then you have to remember that bioaccumulation is we think of it as a pelagic process, but actually it's part of a much larger system. You have sediments involved, you have many layers of food chains, both the pelagic as well as the sediment food web. So with this, the BSAF was born, and that definitely comes right out of the Duluth lab with a number of different people contributing there. Phil Cook was really instrumental in developing that concept, and then a number of papers, and I didn't include them all here. I just wanted to point out that there was a really nice early paper by Gary Enkley and colleagues that looked at the usability of oligochaetes to predict sediment bioaccumulation. And then Larry Burkhart wrote a really clever paper on field studies, basically a directive paper on this is how, if you want to do field studies, you got to do them well, and this is how you do them. And then predicting BAFs, there was a really nice paper comparing different prediction methods involving both BAFs, BSAFs, and other approaches. And so that's a nice paper that Larry and his colleagues at the Duluth lab prepared. The other thing is that, again, Larry is the lead author on this, but again, a host of people from the Duluth lab, they looked at these BSAFs across ecosystems, and they found a really clever finding, actually, that actually you could get very similar slopes, different intercepts across ecosystems. And if you could find those factors that would allow those ecosystems to come together, you could begin to use a few measures of BSAF in a single ecosystem and relate it and get all the BSAFs and BAFs for the entire system if you do a couple of very careful measurements at a new ecosystem. And this is, I don't know how much this is being used, but I found these papers to be just a terrific use use and a very applicable use of really furthering the field of bioaccumulation past the theory and the models and using it in a really applied way. Now, the one thing that ORD is charged with and is often criticized for not doing is to provide guidance to the agency. They often get accused of being scientists off in their own ivory tower doing their own really interesting research. And I happen to know that that's not the case for the Duluth lab or most of EPA, but the Duluth lab in particular, as you've already seen this morning, has contributed enormous amounts of effort and expertise and scientific guidance from everything from water quality criteria, to sediment work, et cetera. Well, they also have they are really the lead part of ORD in providing bioaccumulation advice to the agency. So in terms of providing agency support, this was the Great Lakes Water Quality Initiative that was mentioned by somebody earlier. To determine, and this is the part about determining bioaccumulation factors to help establish water quality criteria, backing it out from fish concentrations. And then also, this is the document that came out in 2000. This is the methodology again for, this is volume 2, it's the development of national bioaccumulation factors. So this wasn't just now applying to the Great Lakes, this was now applying to the entire nation, and this was the methodology for how one would calculate this very specific methodology. And again, this was prepared essentially by the scientists from the EPA lab. They also respond very well, I think, to requests from within ORD itself in terms of wanting some guidance. And so this is an example of some other guidance. And again, this is very detailed. Basically, they said, well, how do you actually do that calculation? This is like an 85-page document that says, this is how you do it. Very, very detailed and very effective and very responsive to the needs of the rest of the agency. And then finally, I want to say that the other thing that I think this is the more recent development, maybe over the last 10 or 15 years, I think the focus of the expertise in bioaccumulation at the Duluth lab has been focused more on working collaboratively and assisting other organizations, not just EPA itself, but helping other organizations with really improving these models as to the best of their ability for regulatory purposes. And so we have many international regulations that we're all quite well aware of. We're well aware of REACH. We're aware of the Canadian domestic substances list. We're aware of the new HTASCA. So there's a number of different the water directive in Europe. These are all regulatory frameworks that need bioaccumulation guidance, and they need it to be as specific as possible. And so these are 3 examples of workshop results or publications where EPA scientists have worked with other scientists from Europe and from Canada and from the US to put together the best possible guidance for how to implement these regulations. And again, that's what the science at EPA is supposed to do. It is supposed to inform and further better regulations to protect the environment from EPA. In terms of future needs, actually a lot has been done, but it's not all done. So those of you that are still at EPA in Duluth, you still have a job, and you still will have a job for some time. And many of the same things that were needed from the aquatic, when we were doing aquatic bioaccumulation from, those early days of, log KOW versus BSAF, we still need some of those kinds of data and parameterizations of models for the terrestrial food chain. So we are nowhere near as advanced on the terrestrial side as we are on the aquatic side. And so that's something that I know that the Duluth scientists have been working on. And these are some of I've listed here, a number of those needs. But it's important to kind of say they fall into 2 categories. We need improvements in the models, their parameterization. We also need better data sets to help validate those models. And so I think those needs are seen for both aquatic systems still and for the terrestrial systems. So I want to finish up by just thanking some of the main players that have they come up all the time in the literature when it comes to bioaccumulation. And these are leaders. They didn't just, add a few pieces here and there. Really, the fundamentals of the accumulation of contaminants in fish really started with Gill's measurement as a grad student and progressed from there. And they're still doing fantastic work. So thanks to them.
time for questions for Deb. Anyone?
To all the people sitting on the steps over here, there's lots of seats.
Questions?
Uh-oh.
So, Deborah, where I grew up on the Great Lakes on the eastern end of the Upper Peninsula of Michigan, following the decline of the lake trout and a number of other things that have been attributed to PCBs, maybe dioxins. One of the things that has happened in the last 5 to 8 years has been an explosion of cormorants. Any comments on effects of PCBs on cormorant eggs?
No, and I don't know the specific story there, but I do know that the Great Lakes ecosystem is such it's so unusual because it's so managed. The fishery is totally managed. The contaminant concentrations are changing all the time, and you're going from overt effects like DDT, breaking eggshells, so getting absolutely no recruitment, to getting malformations, to now getting endocrine disruption in some other ways. So there's all sorts of subtle differences. I don't know if anyone else in the audience can answer your question. Maybe Gary. Gary doesn't want to. Okay.
Any other questions or comments? All right. Well, thank you, Deb.